Good day and welcome once again, still on the fundamental theorem of calculus. But in today's class, we are evaluating these questions. The first one says d dx of the integral of ln t dt from 2x to 3x squared. The second one says d dx of integral 1 over root 3 plus t squared from x squared to x cubed. And then we have the third questions. I have three questions that I want to solve. But you will remember from the previous video, I said that if I have a question like this, if we find ourselves with a question like this, we should remember the second fundamental theorem of calculus. What does the second fundamental theorem of calculus say? It says that the differential of f of x, capital F of x, is equal to d dx of the integral of f of t dt from a to x, and it is equal to what? F of x. That is just basically the second fundamental theorem of calculus. And I said that we should take note of this, where our a will always be a constant and our x will always be a variable. But in previous video, or in the last video, we look at the situation where our x is a function of x, and I said we are going to make use of the chain rule in order to solve that. But if we look at these questions, we will see that something else is happening with our a. Something else is happening with our a, the lower limit of the integral. For the first one, the lower limit of the integral is also a function of x. Same thing applies to the second one and the third one. What happens when I have a question like that? Let's take question number 1. It says we should evaluate d dx of the integral of ln t dt from 2x to 3x squared. When I have a question like that, remember, when we are talking about the fundamental theorem of calculus, we talk about the closed interval AB. So let's assume that's my interval AB. Let's find a spot for 2x and 3x squared on this interval. If this is my 2x and that's my 3x squared, it's just to bring out a means of solving the question. It does not mean that our 2x is less than 3x squared. Neither does it mean that our 3x squared is greater than 2x. Assuming within this subinterval of 2x and 3x squared, I have a point C. A point C there. Let me say that my point C is point 0. And so I will take the integral between 2x and 0, and then the integral from 0 to 3x squared. Again, let me say that does not mean that our 2x is less than 0, neither does it mean that our 3x squared is less than 0. It's just to find a way to deal with that problem. And what does that tell me? My d dx of the integral of ln t dt from 2x to 3x squared will be equals to what? The d dx of the integral from 2x to 0 of ln t dt plus d dx of the integral from 0 to 3x squared of ln t dt. What am I trying to bring out there? Trying to make my a constant. I can see from here now that my A is constant 0. I need to do the same thing to this. In order to do that here, I need to apply the properties of Riemann integral. So I can transform that and have my 0 as the lower limit. But if I would do that, I need to introduce the negative sign. Again, as I said before, if you need to look at the properties of Riemann integral, you can go and check the previous video on the properties of Riemann integral. So d dx of ln t dt from 2x to 3x squared will be equals to what? When this changes and becomes negative, I have d dx of the integral from 0 to 3x squared of ln t dt minus d dx of the integral from 0 to 2x ln t dt. Again, you will remember that I said when we have function as the upper limit, function of x as the upper limit, I said we are going to do what? We are going to perform something like the chain rule. You can go ahead and check the previous video on solving examples of fundamental theorem of calculus 2. You can check that video and see how that takes place. This then becomes what? D dx, or better yet, du dx times the d du of this. Our u now becomes this one, 0 to u of ln t dt, where u is equal to 3x squared minus, so that I will avoid mix up of variables, I can say dp dx times the integral, no, before the integral, times d dp of the integral of ln t dt from 0 to p, and our p is 2x. If u is 3x squared, du dx is what? 6x, and dp dx is what? 2. So this gives me 6x into this. Now is similar to this, d dx of the integral of f of t dt from constant a to variable x, d du of the integral of ln t dt from constant o or 0 to variable u, and that will give me what? Ln u minus 2 into what? Ln p. Same thing applies there. So I have 6x ln, what is my u? 3x squared minus 2 ln, what is my p? 2x. Therefore, the integral, d dx of the integral of ln t dt from 2x to 3x squared is equal to 6x ln 3x squared minus 2 ln 2x. If you need to pause the video, you can pause it so you can look at it again and see how much of this that you understand. Let's go to the second example. Again, in order to solve the second example, we are going to make the same assumption. We are evaluating the differential of the integral of 1 over square root of 3 plus t squared dt from x squared to x cubed. Again, as I said before, our a, the lower limit, is supposed to be a constant for us to make use of FTC2. That is the second version of the fundamental theorem of calculus. And our upper limit should be a variable x, not a function of x. But if it is both functions of x, as I have in this case, just as we did to example 1, assuming that's our interval a to b, we find a spot for x squared and x cubed on that. Again, as I said before, this does not imply that our x squared is less than x cubed or our x cubed is less than x squared. No, but it's just a means to an end. Now, in between that, I'll find a point 0. And so I have the subintervals x squared 0 and what? 0 x cubed. So if I need to work on the interval of x squared to x cubed, it will be the addition of the two sub-intervals. And that tells me, permit me to rub this off, that d dx for the integral of x squared to x cubed of 1 over square root of 3 plus t squared dt is equal to d dx of the integral from x squared to 0 of 1 over square root of 3 plus t squared dt plus d dx of the integral of 0 to x cubed of 1 plus square root of 3 plus t squared dt. And I also said that by the properties of Riemann integral, this changes to negative, and I have this to become what? D dx of the integral from 0 to x cubed of 1 over the square root of 3 plus t squared dt minus d dx of the integral from 0 to x squared of 1 over the square root of 3 plus t squared dt. And again, as we said in example 1, that once the upper limit is a function of x and not just the variable x, we need to perform something like the chain rule. And so this now becomes what? Let u equals x cubed and p equals x squared. U equals x cubed and p equals x squared. So I have this to become what? D du, or better yet, du dx times d du of the integral from 0 to u of 1 over the square root of 3 plus t squared dt minus dp dx times d dp of the integral from 0 to p of 1 over the square root of 3 plus t squared dt. Du dx gives me what? 3x squared into, by the time we take this, according to the FTC2, it says our answer is what? F of x. And what's our f of t? Our f of t is 1 over square root of 3 minus t squared, 3 plus t squared. And so this becomes what? 1 over, that will now be f of u, 1 over the square root of 3 plus u squared minus the p dx 2x into 1 over square root of 3 plus p squared. And so that becomes what? 3s squared over the square root of 3 plus s cubed raised to power 2 minus 2x over the square root of 3 plus s squared raised to power 2. And that gives us 3s squared over the square root of 3 plus x raised to power 6 minus 2x over the square root of 3 plus x raised to power 4. Therefore, d dx of the integral of s squared, the integral from s squared to s cubed of 1 over square root of 3 plus t squared dt is equal to 3x squared over the square root of 3 plus x raised to power 6 minus 2x over the square root of 3 plus x raised to power 4. If you need to pause the video, you can pause it even at this point so that you can take a look at it again. We look at the third one. It follows the same process, just as number 1 and number 2 that we have done. But we can go over it again. But you can pause the video also, try your hands on it, and see if you arrive at the same answer as we would do when we solve the question. You can pause the video, try your hands on it, and see if you arrive at our answer. Question number 3, we are evaluating d dx of the integral of t dt from x to cos x. Again, as I said before, I said we recall our interval a to b, and then in that interval, we find a spot for x and a spot for cos x. And this does not imply, as I mentioned for the first and second one, it does not imply that our cos x is greater than x. That does it imply that our x is less than cos x. In between that interval, I look for a spot 0, and so I have the subinterval x0 and 0 cos x. Again, it does not imply that our x is less than 0, neither does it imply that cos x is greater than 0, but rather, as we said before, it is a means to an end. It is a means to an end. So bringing that into play here, permit me to rub that up also. That tells us that d dx of the integral of t dt from x to cos x is equal to what? Is equal to d dx of the integral of t dt from x to 0 plus d dx of t dt from 0 to cos x. From 0 to cos x. And so, remember that I said this will become negative so that I can have a flip of that interval. And so I have d dx of the integral from 0 to cos x of t dt minus d dx of the integral from 0 to x of t dt. This easily falls into play because my a is a constant 0, and my x is just variable x. So tells me that according to FTC2, it is equal to f of x. But looking at the first half of that question, that solution, I have my d dx. The lower limit of the integral is a constant, which is same as this, but the upper limit is a function of. So as we have been doing before, we perform something like the chain rule. Let u equals cos x, and so this becomes du dx times d du of the integral from 0 to u of t dt minus d dx of the integral from 0 to x of t dt is minus sine x into what? d du of the integral of t dt from 0 to u, and that is also f of u, and that is what? U minus x. Remember, this is f of x, and our f of x is f of t is t, and so f of x will be x. And so this gives me minus sine x. What is our u? Cos x minus x. Can rewrite that as minus into x plus sine x cos x. Therefore, d dx of the integral of t dt from x to cos x is equal to minus into x plus sine x cos. Did you arrive at our answer? If you did, give the video a thumbs up and also like the video. Thank you. God bless you. I see you in the next video.